Hi everyone, my name is Vanitha Ranganeni. I'm the Human-Robot Interaction Lead at Hello Robot, and today I'm going to be presenting some work during my dissertation at University of Washington, supported by my co-authors Varad Dutt, Noah Ponto, and Maya Chakmak. So I want to begin by introducing you to Henry and Jane Evans. They're the stakeholders in this work and have been really critical to the design and development of the AccessTeleopKit. So on the left is Henry. He's a loving husband, father, grandfather, and overall just a generally playful individual, which you'll see some of that later in this work. And Jane, over to the right, is his wife and primary caregiver. She's also a loving mother, grandmother, and friend, and is often at the receiving end of interactions with Henry through Stretch, which is the robot we use in this work, shown in the middle. Henry had a stroke in 2002, and as a result, he is paralyzed from the neck down with limited mobility in his neck and his left thumb. And in this work, he's been playing a critical role in the development. And next, I'll show you a video clip where he introduces himself and the involvement in this work. He is non-speaking, so he did write a narration that we use text-to-speech to overlay on the video.
My name is Henry Evans, a mute quadriplegic since 2002. Recently, I have spent 3 summers exploring different ways to use the robot Stretch. To really appreciate what Stretch does for me, first have someone bind you to your bed so the only thing you can move is your head, and let you lie there for a couple of days. Have them do this when you have a lot to do. Then imagine what it is like to be in this condition for 30 to 40 years. Yeah, it's no picnic. Now imagine that, instead, after 10 years, someone brings you a robot that you can control with a web browser on your computer to scratch your head when and where it itches, feed yourself when you are hungry, and in general travel through and manipulate your environment.
So in this video, Henry used the AccessTeleopKit, which is a toolkit for creating custom and accessible robot teleoperation interfaces based on cursor and click input for controlling the Stretch 3 mobile manipulator shown on the left. We focus on cursor and click input specifically because it can integrate with a wide variety of existing input devices. Some examples shown here that participants in our studies have used are the Kensington Rollerball mouse, the Quad-Joy mount joystick, and the Glasshouse assistive device. And Henry specifically uses a head tracker to move the cursor and also a mouse that he tapes his hand to click. So while several teleoperation interfaces have been developed for robotics, most of these are inaccessible to users with severe motor limitations and often require fine-grained control, which is not accessible. Other works have explored developing interfaces specifically for this population, but oftentimes these interfaces are for very specific tasks or just are fixed in general in their control scheme and what they offer to the user. Our work aims on making teleoperation interfaces accessible to users with unique needs and preferences and enabling customization of the interface to essentially make different interfaces available for a single robot. So in this example, Henry is using the AccessTeleopKit to create his own custom interface. So he begins by deleting the standard layout that we've given him, adding a new panel, which he can add different components to control the robot and see through its camera views. So he adds a number of camera views as well as different button pads for controlling the robot's joints. So for the architecture of the AccessTeleopKit, on the back end, we use ROS2, or Robot Operating System, which is a set of software libraries and tools for building robot applications. We use WebRTC to establish a peer connection between the operator browser, which loads the AccessTeleopKit, and to connect with the robot side. In this work, we specifically apply the AccessTeleopKit to the Stretch mobile manipulator, but the backend can be swapped out for another mobile manipulator as long as it uses the ROS2 ecosystem, and the code is fully open sourced. So Stretch, as I mentioned earlier, is a mobile manipulator with a prismatic vertical lift reaching up to 110 centimeters and a telescoping horizontal arm. It has a gripper payload of 2 kilograms, and overall it weighs roughly 24.5 kilograms. It has a differential drive mobile base with a 2D LiDAR for sensing. The end effector is a 3-degree of freedom dexterous wrist that has a RealSense D405 camera for depth sensing and just more visual input. And then finally, on the head, there's a RealSense D435i camera as well as a wide-angle camera attached to a pan tilt head. The AccessTeleopKit was developed over multiple years of iteration and developed with Henry and Jane, as well as other participants in a variety of studies. It started off in 2020, where Dr. Charlie Camp made the first iteration of the interface, which was then evaluated by Cabrera et al. To establish its feasibility for this population. Later, V. Wen, who was an occupational therapy student at the time, took Stretch along with the interface to Henry and Jane's home to iterate on it with Henry. And at the end of that deployment, Henry actually designed his own version of the interface in Google Slides, which we then went and implemented along with the few customization features to evaluate the feasibility of customization, which led to a second home deployment 2 summers ago, and then a third home deployment this past summer where we developed the prototype of the AccessTeleopKit to iterate on with Henry. And finally, after that, we did an in-lab evaluation in March 2024. In the paper, we go through the design iteration, the insights, everything that we've tested in more detail. But in this work, the core contribution is the third home deployment and the in-lab evaluation, which is what I'll be focusing on in this talk. So starting with the third home deployment, the way this works is we first start with the user's needs assessments and created a prioritized list of tasks. Then we took Stretch along with the AccessTeleopKit to their home, did a 1-week deployment with the participatory design session, and any changes that we could make on-site quickly were done, but any major improvements or new features were done off-site with 3 weeks in between our sessions. We went back for a second session, and this repeated until we had 3 sessions. Henry did a variety of different tasks during the home deployment, but I'm going to focus specifically on him playing with his granddaughter. When we spoke to Jane, she said, "Our granddaughter looks at Henry as an inanimate object, and there's a sadness in that. Henry has shared with me how sad that is." And for the first time ever, he was able to play with his 3-year-old granddaughter via Stretch, where he controlled it so he could play a basketball, build a fort with her, and even play this fishing game that she really liked. And what was really cool about this is that she opened up to him in a way that she hadn't previously. So in this photo, she had a worksheet of games that she could choose to play, and she's showing Henry that they finished playing all their games. And what was particularly touching is actually several weeks after we had left their home, Jane sends a text to me and V with the photo of Henry and his granddaughter sitting on her lap, which she had previously never done. And she said, "Thanks to both of you, our granddaughter is warming up to Papa Wheelie," which is her nickname for Henry. When it comes to back to the AccessTeleopKit, Henry created different interfaces depending on the different tasks. So when he was playing with his granddaughter, he wanted every single camera view, and he had these different versions of the button pads to give him controls for all the joints. But he didn't use any of the autonomous functionality because he wanted to be the main driver of those interactions. Versus when he was handing off Jam to Jane, he used some more of the autonomous capabilities, such as autonomous navigation, and didn't need all of the camera views because he was relying on autonomy. So this shows that several factors influence customization beyond users' functional abilities and preferences, such as the task, the context of the task, and whether or not the robot is in line of sight. After the third home deployment with Henry, we further iterated on the interface and then did a more structured in-lab evaluation over the course of 2 different studies. In the first study, we evaluated customization across 5 participants with varying levels of motor impairments. And in the second study, we had 1 participant do multiple tasks. And all these studies were conducted remotely in a kitchen environment in our lab, and we had users join from all across the US via Zoom, share their screen, and log into the robot interface. So for the first study, we had participants pick up a bottle of juice off the ground and place it on the table that was behind the robot. And what was really interesting from this is that it resulted in 5 very unique interfaces. And all participants also noted that they liked having the ability to customize. In the paper, we go into more details about people's exact reasoning for why they developed these interfaces, but the key takeaway from this is that highly customizable interfaces are valuable, and users' preferences for interface configuration varied widely, even across the same task. In the second study, we had the 1 participant do multiple tasks, and it was in a kitchen environment in the lab. And so for the first task, they were asked to open a drawer, pick up a salt shaker off the island, and put it inside the drawer. For the second task, they were asked to navigate to a microwave on the island and open the microwave. And the third task, they were asked to navigate across the kitchen, pick up the salt shaker off the ground, and bring it back to the kitchen. And what we saw that was really interesting about this, unlike Henry, who created multiple interfaces for the different tasks, this person tried to evolve their interface as they were doing the task to find the one optimal interface. And in the paper, we go into more details about what that process looked like, but the key takeaway from this study is that interfaces can evolve over time, implying that customization is not a one-time event, but rather an ongoing process. So we did show the efficacy of the AccessTeleopKit, but there are limitations and areas for future work. So the main limitation is that when we were testing this in our user studies, majority of the participants who evaluated the AccessTeleopKit were young and daily technology users. And in future work, we want to expand to a broader population of different age groups and people with different levels of expertise in technology. Further, we focused a lot on teleoperation, and we did investigate autonomous navigation, but more autonomous functionality can streamline some of the tasks. And one good way to do this while giving people control and allowing them to define their own custom tasks is end-user programming. So if you're here for the first talk of this session, a lot of those techniques would actually be really relevant to this work. And with that, I'll conclude my talk and take any questions.
Thank you. This is really nice work. I'm Jian Kim from Texas A&M. So I have two questions. One is about the teleoperating. I feel like the robot is somewhat co-located with the user in a way that the user knows the floor navigation, floor plans, and where to reach. So how do you define the teleoperation in this context?
Yeah, so, okay, I can't find the slide, but we actually did test when Henry was not co-located with the robot. So there's multiple aspects to this. There's the robot not being in the same room as him, but as you said, he's aware of the floor plan. But there's another aspect where we actually took the robot to his granddaughter's house, and he stayed at home. And he, in comparison to his home, is not as familiar with the layout and is very different because he's not in line of sight. And that actually influenced a lot of the choices he made in the interface configuration, where when he's in his home, he didn't necessarily choose all the camera views, but he needed all the camera views when he wasn't in an environment that he was familiar with.
I hope that the robot is presenting here at the conference in the future. Yeah. The second one is the physical manipulation is very complex. So even if you are enabling the grabbing and then placing, pick and place manipulation pretty easily with the robots, it is a lot different from like manipulating whisker in the kitchen, and then like chopping on the chopboard is also different. How do you manipulate all these end effects?
Yeah, so right now in this work that I've presented, which was from last year, it was just teleoperation, but we actually did expand on the features and the interface where we have this click to pre-grasp feature where you could click on the object you want to grasp in the camera view. And it doesn't do the full grasping sequence, but it gets you 95% there to really streamline how fast that goes. And actually, Henry really, really liked that feature, and it made things, it really opened up the horizon of the different tasks that he could be able to do. Yeah.
Great, thanks. One more quick question while the speakers trade out laptops.
Hi, really cool work. I was wondering, I know that having the access to the web interface and WebRTC and being able to operate it at a distance is a really powerful tool. Do you envision it also being deployable in like public spaces as opposed to just somewhere with internet access?
Yeah, so right now for being able to use it remotely, you do need to have internet access, but we do have a variation of the interface where if you're in the same space, you can run it offline. So that's kind of the intermediary thing, but currently if you are remote, you do need internet access. Yeah. Cool, thank you.
All right, let's thank our speaker one more time.